Hi students, good morning. So my name is Phanindra and I am working as a physics lecturer in Vignan institutions. So let us continue our topic regarding the chapter laws of motion. So until now we have discussed about what is inertia, inertia of rest, inertia of motion and inertia of direction, Newton's first law, momentum and Newton's second law, and what is impulse and some of the applications regarding the impulse. Now, in this session, let us discuss what is Newton's third. So, from our schooling time onwards, we are very familiar with this Newton's third law. So, the statement is to every action, there is an equal and opposite reaction. So, for every action, there is an equal and opposite reaction. So, it is the statement of Newton's third law. So, consider a horizontal surface in which two blocks are placed. It is the block A and another block B. Right. Now, here action reaction. Suppose a block A exerts a force on block B. So, here action represents, let FA be the force acting on B due to A. Force acting on B due to A, block A. Represents this is an action. So reaction is FBA. So FBA bar is force acting on block A due to the block B. It is the reaction. So force acting on block B due to A is in this direction. So FAB, and force acting on block A due to B, that is FBA, is in this direction. According to this Newton's third law, for every action there is an equal and opposite reaction. Hence, therefore, FAB equal and opposite. So FAB bar is equal to minus FBA bar. They are equal in magnitude but opposite in direction. Okay, so here if the block, so according to the statement, if we apply a force on anything, there should be an equal and opposite reaction also. So here block A is applying the force on block B. The same force, that is in opposite direction, block B is also applying on the block A. So according to Newton's third law, for every action there is an equal and opposite reaction. So FAB is equal to minus FBA bar. So let us see some examples from that which we can clearly understand. So what the Newton's has explained us regarding the Newton's third law. So before going into see some examples, let us see what is the limitations of Newton's third law. So Newton's third law is not strictly applicable for interaction between the bodies which are separated by a larger distance in the order of astronomical units, that is in the form of the light years. So this Newton's third law cannot be applied when the distance between the two objects is very large. So it is the first limitation. It is the first limitations where Newton's third law cannot be applicable if the separation between the two bodies is very large. And the second limitation is it does not apply when the objects move with velocity of light. If the objects are moving with velocity of light or nearer to the velocity of light, the Newton's third law cannot be applicable. And the third limitation is it does not apply where the gravitational field is very strong. Newton's third law cannot be applied when the gravitational fields are very strong. These are the limitations where we cannot apply Newton's third law. So first one is if the distance are much larger between the two bodies, that is in astronomical units. And the second one is if the bodies are moving with a velocity nearer to the velocity of light, Newton's third law cannot be applicable. And the third one is it cannot be applicable where the gravitational fields are very strong. So next one, according to Newton's third law, which says that for every action there is an equal and opposite reaction. So now let us see what is the characteristics of this action and reaction. So the first characteristic says that action and reaction are equal in magnitude but opposite in direction. These action reaction pairs are equal in magnitude but opposite in direction. So therefore we can write it as FAB bar is equal to minus FBA bar. Force acting on block A due to the block B is equal and opposite to the force acting on the block B due to the block A. Therefore, FAB is equal to minus FB. And then the next characteristic says that action and reaction does not act on same bodies. Therefore, they do not cancel each other. So, consider two blocks. So, let this be the block A and let it be the block B, A and B. So, FAB is the force acting on the block B due to A, FAB. Force acting on the block B, on the second block due to the block A. And FBA is the force acting on the first block, that is A, due to the block B. So here the action and reaction takes place on two different bodies. Hence they do not cancel each other. Okay, and the third one is action and reaction pairs always exist in pairs and only exist as long as the other exists. So this action reaction forces always occurs in pairs, right? So whenever there is an action, there should be a reaction. Whenever there should be a reaction, there should be an action. So they exist only in pairs. And the last characteristics of action reaction is when taken together, action and reaction, we call them as internal forces. So when taken together, this action and reaction forces will be the internal forces of the body. So these are the main characteristics of the action reaction pair that we should understand so that we can solve the problems. Okay, so without understanding these characteristics of action and reaction, we cannot understand how Newton's third law can be applicable on the other processes. So the main characteristics of this action reaction pairs are action reaction pairs has equal in magnitude and opposite in direction, and action reaction does not act on the same body, as they do not, so they act on two different bodies, so they do not cancel each other. And the action reaction pairs always exist in pairs. So if there is an action, there should be another reaction. Okay, and when we take the action reaction together, these action reaction are called as internal forces of the body. So the examples of Newton's third law, how we can understand this Newton's third law very clearly. So by observing this example, we can understand the Newton's third law. So first consider an example in which a book is placed over the table. Here a book placed on the table, the weight of the book will act downwards. So this weight is supported by the table. If this table does not support the weight of the book, then it will break. So the weight of the book acts downwards. Similarly, the weight is withstood by the table. So the weight acts on the table and its supports acts on the book. Action, reaction. Similarly, in this example, a cannon fires a bullet. Bullet fired from a gun or a bullet fired from a cannon. Here you can see in this animation that whenever the bullet or the cannon fires the bullet, so bullet moves forward and the cannon moves backwards. So for every action, equal and opposite reaction. As the bullet moves forward, the cannon moves backward. So action, reaction. And similarly, in this example, So a rocket is moving upwards. So here the flame or the fire coming out from the nozzle of the rocket will be in the downward direction, so that the rocket will move in upward direction. Action, because of the flame it is coming downwards. Flame is coming downwards. Due to the flame that is coming out of the nozzle of the rocket is moving upwards. Similarly, in this example, so whenever you are walking on a road, the feet of yours, or the feet of the tiger walking here, moves the road backwards or pushes the road backwards. In turn, the road pushes you forwards. So here the action is you are pushing the road backwards while walking, and the reaction is the road pushes you forward. So I think from this example you may understand the what is Newton's third law, what is action and reaction. So for every action, there is a equal and opposite reaction. Similarly, you can take many examples. When you are trying to hit a wall, so you are hitting a wall, that means you are applying a force on the wall. So there is some disturbance or there is some damage in the wall. Similarly, so there is some pain in your hand also. So when you are applying a force on the wall, equal and opposite force is also applying on your hand due to the wall. So force applied by you on the wall is the action, and the force applied by the wall on your hand is the reaction. Okay, therefore for every action there is an equal and opposite reaction. So next class, how to calculate the change in momentum of the body. So from here onwards we are considering some objective problems. For solving some of the objective problems, we will discuss or we will calculate the mathematical formula for some of the cases. So for that, initially let us go to calculate the change in momentum of the body. So from our previous discussions, we know that the momentum of your body is denoted by P, which is given by mass into velocity. P is equal to m into v. So here consider a block which is moving with a velocity vi, has a momentum pi. So by some collision or by some applying a force, let the block moves after a small time interval of delta t. Let the blocks moves with a momentum of pf or moving with a velocity of v final. Okay, now we need to calculate what is the change in momentum of the body. So change in momentum is equal to change in momentum, or delta p is equal to final momentum minus initial momentum. Final minus initial, always the change is final minus initial. So final momentum minus initial momentum. Therefore delta p bar is equal to p final bar minus p initial bar. Why I indicating the direction? So momentum is a vector quantity which has both magnitude and direction. Therefore delta p bar is equal to p final means m into v final or minus m into v initial bar. Okay, that is the change in momentum of the body. So if we want to calculate the magnitude of the change in momentum, that is delta p bar is equal to find the magnitude of the two vectors or the subtraction of the two vectors, we have studied a formula in motion a plane. So difference between the two vectors, that is delta p is equal to, according to parallelogram law, p final square plus p initial square minus 2p final into p initial into cos theta. It is the magnitude of change in momentum of the body, where theta is the angle between p final and p initial. Theta is angle between p final and p initial. angle between the P final and the P initial. So in this manner, we have to calculate the change in momentum of the body. So as we discussed this earlier, but discussing here is regarding to solve the some of the objective problems. We will see some cases where the problems can be asked, such that we can calculate the formula. Okay, students, now let us move to some cases regarding the how to calculate the change in momentum of the body. Here is the first case. So consider a body of mass m moving with a velocity v I cap. That is, the direction of the velocity is in the direction of the positive x-axis, and if it hits a rigid surface or a wall and comes to rest. So let us draw the diagram. Let us consider this as a wall. Okay, so now a ball is moving in the direction of vi cap. So in the positive x-axis direction, let the ball of mass m, that is moving with a velocity vi cap in the positive x direction. So after hitting the wall, it comes to rest. That means final velocity v final is equal to 0. Then we need to calculate the change in momentum of the body. So change in momentum is equal to P final minus P initial. So that is equal to P final is as V final is 0, 0 minus P initial means M into V I cap. That is equal to minus MV I cap. Here minus I cap means the change in momentum is in negative x-axis. So magnitude of the change in momentum delta P is equal to M into V. If the ball hits the wall and it stops and comes to rest means. So in another case, it may be asked like this. If the ball hits the wall, let us consider another case. So the same ball of mass m moving with a velocity vi cap. So after hitting the wall, it comes back in the same direction. That means with the same velocity in opposite direction. So minus vi cap. Here v final velocity is 0. In the second case, now we are considering if the ball hits the wall and coming back towards in the same direction with the same velocity, in opposite direction with same velocity. So minus vi cap. Now we need to calculate the change in momentum. So change in momentum is equal to P final minus P initial. So that is equal to, so P final means minus MV I cap, okay, minus P initial means MV I cap. So that is equal to minus 2MV I cap. So the change in momentum, the direction of the change in momentum is in the direction of negative x-axis. Therefore, magnitude of the change in momentum delta is equal to 2mv. Okay, now here we consider if the ball moves back with same velocity. So in the next case, let us consider what happens to the change in momentum of the ball if the ball hits the wall with a velocity vi cap or v1 I cap and rebounds back with a velocity v2 minus v2 I cap. Rebounds means negative direction. Initially it's moving with positive x-axis. Now rebounds back means negative minus I cap. So change in velocity delta p is equal to p final minus p initial. So final means here mass m into minus v2 I cap minus m into v1 I cap. So that is equal to m into v2 minus v1 minus I cap. Minus I cap denotes the direction of the change in momentum. So delta p. So magnitude of the change in momentum is m into v2 minus v1. Okay, students, now let us calculate the change in momentum in case of a projectile motion. So, as we studied the projectile motion in our last chapter, the kinematics or motion in a plane. So, consider it as x-axis and a y-axis, and this is the point of origin O. From this point, if we throw a ball or a body with a velocity u making an angle theta, then the path of the projectile is parabola. Right. So at this point the velocity can be represented into two components here, v cos theta and along this v sin theta. Right. So let it be the highest point where the velocity across the uh, only the velocity component across the horizontal direction is present and the velocity vector along the vertical direction is 0. So velocity is in this, which is v sin theta, right? And at this point the velocity can be represented into two components here, v cos theta and along this direction v sin theta. Okay, now let us calculate the change in momentum of the body. In the first case, change at the point from the initial point to the final point, between the point of, so change in momentum between highest point and a point of projection. Highest point and the point of projection. So change in potential, change in momentum is equal to delta p is equal to p final minus p initial, that is equal to, the final is at the highest point, momentum will be mv sin theta minus initial, so or mv sin theta I cap minus initial is the final, and the initial at this point it is mv, sorry, so here mv cos theta, actually it is mv cos theta, and here also mv cos theta. So mv cos theta I cap plus mv sin theta j cap. So mv cos theta I cap, mv cos theta I cap get cancelled. The change in momentum is mv sin theta j cap. So the change in momentum between the 2 points, the highest point and the point of projection, is mv sin theta j cap. It is in the direction of positive y-axis. Similarly, I need to calculate the change in momentum between the point of projection, and striking point, and the striking point. So change in momentum is equal to final minus initial. So final momentum is mv cos theta I cap, as it is in negative, so minus mv sin theta j cap. It is the momentum at the striking point, that is final momentum, minus initial momentum, which is mv cos theta I cap plus mv sin theta j cap. Right. So from here mv cos theta get cancelled. So change in momentum is equal to minus 2mv sin theta into j cap. So magnitude of change in momentum is equal to mod delta p is equal to 2mv sin theta. It is 2mv sin theta, and the direction will be in negative y-axis. Minus j cap represents negative y-axis. So this is how we calculate the value of change in momentum in a different cases. I think you can solve some of the problems. How do we calculate the change in momentum in case of projectile motion or in case of the examples that I have given in the previous one. So now let us see some of the applications where we use Newton's third law. So here is the one of the application gives, if a gun fires a bullet of mass m and each bullet is moving with a velocity v, and the rate at which the gun fires the bullet is n bullets per second, then the force required to hold the gun without recoil. So what is meant by recoil? We will talk later. Without recoiling, that without pushing us. So, or what is the force required to stop the gun without moving backwards? So, according to Newton's third law, for every action there is an equal and opposite reaction. Therefore, force with which you have to hold the gun is equal to force with which the bullets are moving forward. So, force with which required to hold the gun is equal to force is equal to, we know that force is equal to mass into acceleration. But here we have given that mass of the bullet, velocity of the bullet, and also the number of bullets are moving per second. So for a time t, the number of bullets will be n for each second. So the formula of force will be n into m into v. So mass into acceleration. Acceleration is nothing but change in velocity by time. So number of bullets moving per second is n. So with a velocity v. So F is equal to n into m into v. So this is the force that is required to hold the gun without recoil. Okay. Okay. Now let us move on to the next case, in which a metallic plate of mass m is held in the mid-air by firing the bullets with a gun of mass m, and each bullet is moving with a velocity v. And for every second there n bullets are moving or hitting the plate. Now the condition is, if the bullet hits the metallic plate and drop dead, so then the condition will be, so the weight of the body block or the weight of the metallic plate mg should be equal to, or by hitting the plate should be in the mid-air only. Such means the force by which we are firing the bullets should be equal to the weight of the plate. So mg is equal to force produced due to the gun, that is equal to n into m into v. To hold still the metallic plate in the mid-air, the condition is mg is equal to weight of the body should be equal to force which is produced by firing the bullets, that is n into m into v. In the second case, if the bullets are dropped or rebounded with the same speed by hitting the plate, after hitting the metallic plate, the bullets are coming with the same speed. So the weight of the body should be equal to change in momentum. So weight of the body mg should be equal to change in momentum, as we have studied earlier. Change in momentum after rebouncing back is 2 into n into mv. So this is the condition where the bullet have to rebound backwards. Okay students, now let us move on to the next application. So here a gravel is dropped vertically at a rate dm by dt on a conveyor belt. Here you can see that a conveyor belt, a gravel is dropping on the conveyor belt such that a belt is moving horizontally. Then the extra force required to maintain this belt with constant speed. So here you can observe that in this diagram. So the external force or the extra force required to move this conveyor belt with a constant velocity. So from the Newton's second law, the net force acting on a body force is directly proportional to rate of change of momentum dp by dt, or force F is equal to dp by dt. So here momentum is mass into velocity. So F is equal to dmv by dt. Here velocity is constant. The force required to keep this velocity constant. So velocity should be constant. So v into dm by dt. Therefore the force required to keep the conveyor belt moving with a constant speed is F is equal to v into dm by dt. So these are the some applications regarding the new change in momentum of the body, or the regarding to how to solve the some of the problems. So in our next session we will discuss uh, law of conservation of momentum and continuing by some of the problems. Okay, thank you.